In exercise 2110, we're starting to do some syntheses with carboxylic acids and their derivatives. Now here they're requiring you to name some things, or to draw some things from their names, in addition to accomplishing the synthesis. And so in this first one we have ethanol. Eth means you have two carbons, an is all single bonds, and all means you have an OH. And since that molecule is symmetrical, you can put the OH on either of the carbons. So that's ethanol. Acetic acid is the common name for ethanoic acid. And so you still have the two carbons, you just have a carboxylic acid on the molecule. Acetic acid is vinegar. This is an interesting reaction because you're turning drinking alcohol into vinegar. So how do you do that? Well, if you notice here, you only have one bond to an oxygen. Here you have three. You're increasing the number of bonds to oxygen. And so you're going to use an oxidizing agent. And here, because you're oxidizing it as far as you possibly can, all the way to a carboxylic acid, you would use a strong oxidizing agent. So one of the ones you'd want to remember for those is Na2Cr2O7, that's sodium dichromate, and you'd always use that in an acid-water wash, so water with some sulfuric acid. We do that. If you remember, what we learned from the previous chapter was if you have a primary alcohol, like this is, because the carbon here is only bonded to one other carbon, the carbon that has the OH on it, you can oxidize it to an aldehyde. So not quite as oxidized, this only has two bonds to oxygen, this has three, by using pyridinium chlorochromate, PCC, that weak oxidizing agent. But here, that's if you only want to go to the aldehyde. Here we want to go all the way to the carboxylic acid, and so we use a strong oxidizing agent. And this reaction actually happens if you just leave any sort of drinking alcohol out in the air, because oxygen itself is not as strong as sodium dichromate, but it is an oxidizing agent, oxygen, because O2 is often drawn as like this, but really that's just one resonance structure. The other resonance structure is a diradical, where one electron is going there. So you have unpaired electrons on both of these, which makes it really reactive, and you can use it to form new bonds to oxygen. And so this reaction is the reason why if you leave wine out, it eventually turns into vinegar, if you let it expose it to oxygen in the air. All right, B, toluene. Toluene is a derivative of benzene. It's one of those derivatives whose names you'd want to know. It's methylbenzene in the IUPAC, or yeah, if you were to treat it like a normal branch. So that's toluene, and then what we want to turn that into is benzoic acid. That's another one of the benzene derivatives. If benzoic acid is benzene, but with a carboxylic acid functional group coming off of it. And actually, just so we can sort of see the connection better, I'll draw this here. So if you compare these two structures, toluene and benzoic acid, what you will notice is you have the same number of carbons, so you have 6 carbons in the ring, you have 1 carbon outside of the ring, but where it's different is this has 0 bonds to oxygen, and here you have 3. So you've oxidized it, and you've oxidized it as much as you possibly could, all the way to a carboxylic acid. So you'd want to use a strong oxidizing agent, and we just saw one, sodium dichromate, Na2Cr2O7. And you'd do that in an acid-water wash, so water, and sulfuric acid, H2SO4. And you'll remember that reacts at the benzylic position, which is really reactive. So long as there is a hydrogen on the benzylic position, you can do these reactions there. You can oxidize it. It doesn't matter what other carbon chains there are. It will saw them all off, the strong oxidizing agent, and just turn the product into benzoic acid. But you do need at least one hydrogen on the benzylic position, as we discussed in a previous chapter. The mechanism for how it works is not entirely known, but it's thought that it occurs through a radical reaction where the first reaction has to do with ripping that hydrogen off. So if there's not a hydrogen, what people do know is that if there's not a hydrogen there, the reaction won't work. So here on toluene, you have that hydrogen, you see more bonds to oxygen, so you use a strong oxidizing agent, and that turns the benzylic position into a carboxylic acid. All right, benzene, the vapors coming off of gasoline. famous aromatic molecule. And we turn that into benzoic acid, which we just saw previously. It's the benzene derivative of carboxylic acid on it. So if we want to make this transformation happen, what can we do? Well, the first thing you'd notice is we have 6 carbons here, 6 carbons here, but at the product there's 1 extra carbon. In other words, we're making a new carbon-to-carbon bond. Now, there are a few ways to do that. Let's just organize our thoughts. We're getting toward the end of Organic Chemistry 2. What are all the ways we've learned to make, what are the most common ways we've learned to make carbon-carbon bonds? So we have, in this chapter, we've introduced cyanohydrin, or like, you can do nitrile, you can use a cyano group as a nucleophile, right, and make a nitrile. And that brings a carbon in that you can, that sort of has a functional group built in. You could use a Grignard. That's a strong carbon nucleophile, or you could use a Gilman reagent. That's a weaker carbon nucleophile. All of these make carbon-to-carbon single bonds. Then you could also do a Friedel-Crafts. That's a carbon-to-carbon single bond to benzene, kind of specific. You could do a Diels-Alder. Diels-Alder makes a ring, makes 2 carbon bonds and forms a ring. You could use the Wittig reagent. That would make a carbon-to-carbon double bond. So those are a few of the carbon-forming reactions that we've learned, and some of them are new in this one. So here you see a sigma bond. So you might be tempted to think about the cyano groups, the Gilman groups, or the Grignard reagents or the Gilman reagents. But the crucial thing here is that that single bond is connecting the carbon to benzene. So that's a very special case. It's hard to make benzene react. Benzene is aromatic, so it tends not to react, and you have to use a special recipe to make it react. That's where the Friedel-Crafts comes in. You're making a carbon-to-carbon single bond to benzene. So of all those carbon-to-carbon bond-forming reactions, we're going to use the Friedel-Crafts. Okay, well, what is the recipe for Friedel-Crafts? You have to think about how many carbons you want to add, and here we just want to add 1. So you take that carbon, and since we don't have to worry about, since we don't have to worry about carbocation rearrangements, we can do Friedel-Crafts alkylation rather than Friedel-Crafts acylation. Right? You can't do Friedel-Crafts alkylation if you could get carbocation rearrangement that you don't want. You'd have to do Friedel-Crafts acylation and then do a reduction in that case. But since we only have 1 carbon, the carbocation that forms in the mechanism has nowhere to go, and we could do CH3Cl. This Cl is going to interact with the catalyst AlCl3, and that's going to put a methyl group onto benzene. So we still have our benzene, but now we have a methyl group on it. In other words, after that reaction, we create toluene. So there is our Friedel-Crafts. Now, once we have Friedel-Crafts, once we have done that, it's really the same as the previous exercise. We're trying to turn toluene into benzoic acid. And you'd notice we have a benzylic position now with hydrogens on it. It has no bonds to oxygen. Here we have 3 bonds to oxygen, so you'd want to use a strong oxidizing agent like sodium dichromate in acid and water. And that will that'll oxidize that carbon all the way to a carboxylic acid. So the whole recipe here would first be methyl chloride, or chloromethane if you prefer, with AlCl3, and then followed by sodium dichromate in an acid-water wash. And that beautiful recipe would make that transformation happen. You could turn the vapors of gasoline into benzoic acid, which is sometimes used as a preservative in foods. All right, 1-bromobutane, we want to turn that into pentanoic acid. Well, here, this is a branch. Our backbone starts with bute, so that's 4 carbons. 1, 2, 3, 4. AN, all single bonds. E, hydrocarbon. Looking good. Now, I can number this however I want. I'm going to number it 1, 2, 3, 4. On carbon number 1, we have a bromine. So that's going to come off here and Br. So there's 1-bromobutane. Next, we're going to have pentanoic acid. Pent, 5 carbons. So 1, 2, 3, 4, 5. AN, all single bonds. Oic acid means we have a carboxylic acid. They don't give us a number for where that should go because carboxylic acids always go at carbon number 1. So if we sort of, again, number it left to right, that would be right there. So we have 1, 2, 3, 4, and 5. So when you compare these two, one thing that should pop out to you, maybe a couple things, one thing that should pop out to you is that you have a different number of carbons, 4 on the left and 5 on the right. So we're going to have to do some sort of carbon-to-carbon bond-forming reaction. And the second thing is that you've done an oxidation. Right? You have a lot of bonds to oxygen here that did not exist in the starting material. One last thing. You look at a bromine, you see the halogen, and halogens should remind you of leaving groups. So you see a halogen, you're like, leaving group. I could do any sort of substitution or elimination reaction with that. Okay, well, what do we have to form? Now, if you sort of think of this as adding on the end, you can imagine having 1, 2, 3, 4. Those carbons being like these carbons here. In other words, you've added a carbon on the very end. And that could make sense because you have a leaving group here, so you can bring a carbon nucleophile, and this is the bond you would form. Now that's a carbon-to-carbon single bond. We drew out the different ways to form carbon-carbon single bonds above. You can use a cyano group. That makes a carbon-to-carbon single bond with a sort of functional group built in. You could use a Grignard. That makes a carbon-to-carbon single bond, but there's no functional group built in. You could use a Gelman reagent. And that is also, it makes a carbon-to-carbon single bond with no functional group built in. Remember, Grignards you'll recognize because of MgBr, the Gelmans you'll recognize because of the copper lithium. Because copper is more electronegative than magnesium, this creates a smaller charge on the carbon, and so a weaker carbon nucleophile. So it would only react once with a carboxylic acid derivative, whereas a Grignard would react twice. So these all make carbon-to-carbon single bonds. You can also do a Friedel-Crafts, but here we don't have benzene, so you're not forming a single bond to benzene, so you wouldn't do the Friedel-Crafts. Okay, well, which one of these would work? Technically, you could do any of these and get the answer, but the way that's most efficient is to use the cyano group, because you'll notice that the carbon that you bring in is not just a CH3. It has a functional group built on it, and the cyano group also has a functional group built in, and it's easier to convert one functional group to another often than it is to just create a functional group out of thin air. So the cyano group is going to give us the simplest, most efficient way to transform this. I'll walk through how you could do it even with a Grignard reagent, but let me first show you the cyano group. So if we treat this with sodium cyanide, and remember that's usually how you'd see it. For me, if you wrote CN-, perfectly fine, I really don't mind. But if you see that, you would almost never see that on a standardized test like a PCAT or a DAT or an MCAT. This negative charge by itself is very reactive, so it's often stabilized with a cation like sodium, and it's all written together as NaCN. The capital C next to capital N implies the triple bond there. So that's the first thing, and then what this would do is the carbon nucleophile would end up swooping in, attacking this carbon, kicking the bromine off. So you'd have 5 carbons now. Instead of the bromine, you have this other carbon and 3 bonds to the nitrogen. So this is our first step. Now to get from here, from this nitrile to the carboxylic acid, we've seen this before, it's just the hydrolysis. All you'd have to do is H3O+. And we walked through the mechanism for that in the previous video, the reactions for nitriles. How ultimately this oxygen, and you do a proton transfer to break one of these pi bonds, well, to turn this into a better electrophile. And then the water comes in and attacks this. The oxygen in the water ends up turning into one of the oxygens. You get an imine, and then the imine hydrolyzes, and you get a sort of carboxylic acid. So we drew the mechanism for that in the previous exam. But you can see in 2 steps you can make this transformation happen. You could just do NaCN followed by the hydrolysis of a nitrile. Okay. What if you didn't do that? What if you wanted to do a Grignard reagent, or if you forgot about using a cyano group as a nucleophile? Well, we're only adding 1 carbon, and so you might be tempted to just do methyl magnesium bromide. So this carbon would act as a nucleophile just like the cyano group would. And here you kind of run into a mess, because you have an alkane, and alkanes are not really reactive. In fact, there are only 2 things you can do with alkanes. You can burn them, turn them into carbon dioxide and water, and you can treat them with a radical. And so this is really inefficient. If you treated it with a radical, something like NBS and light, the bromine would go on the most substituted position. So you'd get a mess of different molecules where the bromine, because in the middle here, you have 3 carbons that are all secondary. So you get the bromine adding on each one. Now most of them would add on this second to middle one. And since the molecule is symmetrical, that'll increase your yield a little bit, but you'll still get a little bit of a loss by having a bromine there. If it does add, you can take the molecules where the bromine added right next to the end on the penultimate carbon, and you can do an elimination. Now, technically you want the pi bond, to form over here. That's the less substituted pi bond you could form. The other elimination product you could get here is the pi bond going the other way. And if this doesn't make sense, I'd be happy to send you a video on elimination. I have a whole playlist of them. If you get the less substituted alkene, that's the Hoffman product, you would have to use a bulky base to make that happen. And so potassium terbutoxide would be a bulky base that you'd want to be familiar with. Then we want oxygens on the very end, so we'd have to add an oxygen here. The way you can add an oxygen on the end is by a hydration. You'd add OH there and then H on this other carbon. So you're adding water, so it's called a hydration. And in that case, the H went on the more substituted carbon. That's anti-Markovnikov addition. To do anti-Markovnikov addition, you first use borane in THF, followed by hydrogen peroxide and sodium hydroxide. That's hydroboration oxidation. So once you have that, you have a primary alcohol, and you can oxidize it to your carboxylic acid using a strong oxidizing agent, like sodium dichromate, Na2Cr2O7, in an acid water wash. So this is definitely a much longer recipe. You can see how simple and efficient it is just to use the cyano group, the cyanide nucleophile, followed by a hydrolysis. But if you wanted to do it this other way, first you'd have methyl magnesium bromide, followed by a radical reaction, NBS, N-bromocyclohexane and light, followed by Hoffman elimination using potassium terbutoxide, followed by a 2-step reaction of hydroboration oxidation. So first you'd add the boron and the hydrogen, then you'd replace the boron with an oxygen, and last but not least, you would oxidize the alcohol you have. So that's another option. You could do this 2-step one, or if you prefer, a much more expensive and inefficient 6-step transformation. So it pays to know the differences between the carbon-to-carbon bond forming reactions. All right, ethyl benzene, we're trying to turn that into benzoic acid. Well, ethyl benzene is just a benzene ring with an ethyl group on it. They don't tell you where the ethyl group has to go, because anywhere you put it, the molecule symmetrical. You could just rotate it like a dial, and it'll end up on another position. So we're trying to turn that into benzoic acid. And when you see this, the big difference you'd want to notice is that you have no bonds to oxygen here. You have 3 bonds to oxygen here. So you want to do an oxidation. So long as there is a hydrogen on the benzylic position, you can use sodium dichromate in an acid-water wash. And that will saw off all the other carbons. Those will leave. This will leave as carbon dioxide. It'll bubble away, and what's left of the carbon chain will just be the benzylic carbon, and it will turn into a carboxylic acid. You'll replace all of its bonds with bonds to oxygen. Okay, next, bromocyclohexane. So we have not benzene, but just cyclohexane and a bromine on it. And we want to turn that into cyclohexane carboxylic acid, sort of the non-aromatic version of benzoic acid. Well, this is really similar to something we've seen before. We have here a bromine, so that's a good leaving group, and we have here an extra carbon. So we need to form a new carbon onto that molecule. Now, you can do this in a couple ways. You might be thinking, well, I'm clever now. Now we've learned to use the nitriles, or to use the cyanides. So maybe you could treat this with sodium cyanide. You'll do an SN2 reaction that replaces the leaving group with the cyanide, and then you can just hydrolyze it using acid, and that would work. So one possibility is first sodium cyanide followed by H3O+. So definitely a possibility. Another possibility that's kind of fun is you could turn this into a Grignard reagent, plop some solid magnesium in there, and then react this with carbon dioxide. Because if you have carbon dioxide gas, and the advantage of this is, first, it's just fun to do, but it's the carbon dioxide is very inexpensive, although the Grignard reagent is a little bit of a pain to work with. But this nucleophile can attack the carbon there. This opens up, and you could see how you would get the carboxylate, the ion, and then just do a water wash. So maybe it has that extra step, but it's worth mentioning. It's another way to make this transformation happen. So you could do solid magnesium, followed by carbon dioxide, followed by water. And who knows, I'm sure there are other ways you could do this too. You could, to make this transformation happen, but for now, these two I think will give us enough perspective on how to make that happen. All right, F, bromocyclohexane, and we're trying to turn that into cyclohexane carboxylic acid. Oh, that's the one we just did. Okay, so that was the last of this for this video.